Indiana University Network Science Institute, which he's going to tell you a little bit about. Dr. Yan worked as a postdoc at University of Southern California and is also a graduate fellow at San Jose Institute, and then he did his PhD work at University of New Mexico. And now he's at a super new prestigious place here at IU. So I'll let him tell you more about this and his work. Thanks a lot.
Thank you so much, David. So as he mentioned, before we dive into the technical details, I'll first introduce my home institute, which is called IUNI for short, Indiana University Network Science Institute. So what is this mysterious place that everybody's been talking about? So if you just search for IUNI, you'll find that in the Google map, about 1.5 miles north to here. So not too far away. And if you look at the street view, you'll see this little cozy house, which is our where we work at. In fact, we are just getting started, and we'll be having our opening ceremony next Thursday. So everybody's welcomed. So we might not have a big house, but we have plenty of yard spaces, as you will see, which has been mostly utilized by friendly animals in the neighboring woods at the moment, but we certainly welcome more human companies. And you can also go to our website, and there's resources for data sets and what people are doing. Like I already see a few of those faces appearing here in the audience, and you can see what's going on in the announcements. So if you cannot make it on Thursday, there's another talk. I think it's one of the last network science talk series this semester. I think in IMU next Monday, and we'll have a reception after that as well. So, and the one before that is right here, so you cannot miss this one because you're already here. So let's get back to my slides. Oh, I forgot to mention there's also a faculty affiliate retreat in May. I heard they're having difficulty recruiting attendees, so if you're interested, you have time, so please consider that as well. Because at IUNI, we really encourage interdisciplinary collaborations, and it's very good for everybody to get together from, all different departments, and good ideas came out of, the clash of ideas. So my research at IUNI mainly focused on developing methodologies as well as models and algorithms for practitioners in various different disciplines. And so my expertise has two main areas. One is community detection algorithms. The other is dynamical processes. So in this talk, I'm trying to put those two pieces of my work into a single unifying framework through the idea of graph transformation. And the content of this talk is based on my work at University of Southern California, as well as the new collaboration I'm starting right now with Cody Bonner and Ashwin here at IU. So let's start from the very basic ideas. So what do we study at the uni? Well, networks. And you probably know these are made of vertices and edges. You can represent them as adjacent matrices. And a lot of us like them because they are very flexible model. They are visual. We are all visual animals. But also, this powerful abstraction gives us mathematical objects that we can define, derive, and prove theorems about them. And among a lot of the aspects of network science, today we're going to focus on centrality and community structures of these networks. So here's the two examples of network modeling a real-world system. On the left-hand side, we have a co-author network, where each node is an academic author, and links between authors represent they collaborated on publishing certain paper. And on the right-hand side, we have a multi-layer transportation system of Great Britain. I think down there you have airline connections, you have railway systems, and long-distance coaches on the top. So here I've already shown some idea of what centrality means. So on the left side, the size of the nodes is proportional to its degree centrality. which I will explain in more details. And the colors of these, blue and red divisions correspond to certain ideas community structure in these networks. So what are vertex centralities? These are typically used to rank the importance of each individual vertex in the system. So there's a whole list of possible measures you can use. You can consider everybody the same, being uniform. You can use degree centrality, which is what I'm showing in this toy example as well. You can use eigenvector centrality, page rank, which is Google's invention, used a lot these days. Petunia centrality, and the list just goes on. Similarly, for community structure, you also have different kinds of definitions. So in this talk, we're going to mainly focus on the idea of community being densely connected within, where sparse edges that connects across different communities. So according to this definition, you can come up with minimum flow cut, conductance, ratio cut, blah, blah, blah. And I'm not going to go through all of these. So as a practitioner, so suppose you want to use some of those network models in your research. So how do we choose among these, some endless lists of possible measures? So here on the coastal network, you can do degree centrality, as I said before. You can also use this, which you bias toward a certain group of nodes. In this case, this bunch of people who work in epidemiology, giving a much more bias, so they show up much bigger. For community structures, different measures give you different partitions. So here you can, I think this is the conductance cut. You actually separate out the air lane connections from all the others. By the way, these interlayer connections from airway to train are collected by this wonderful data set where basically counts how many times you spend switching these different modes of transportation. Or if you weight that and in certain other ways, you end up detecting this remote region in the northwest of Scotland. So which one makes more sense? Right? This is a dilemma. And so as network scientists, we usually just say, you as a domain expert should pick based on your knowledge of the problem. And if you don't follow the best practices, you pick something that's not appropriate, that's your fault. But is that the whole story, right? So we came up with these new measures, like every other month or so. The list should go, I'm just showing the sort of tip of the iceberg up here. And even ourselves have a hard time sort of understanding the relationships in terms of when is it better to use it, under what conditions, and how is one related to the other. It's a total mess out there. So in this talk, we're going to try to remedy this problem a little bit by proposing a unifying theoretical framework. So this is a sort of theoretical approach to put these different measures into a coherent sort of basis for comparison. And how do you do that? My approach here is using dynamical processes on networks. So dynamical processes on networks does not mean the change of network structure in this particular case. I'm talking about, given fixed network topology, you can model different systems, like traffic flows or epidemics, different kinds of stuff. Sometimes the network you already observed is a result of such dynamical process already. So like the internet structure that you see in a lot of research is actually the result of web crawlers. And they have different rules of how to sample the network structure. And the sort of big motivation behind all of this is that the structure that everybody thinks that's important in their studies is actually the combination of the network topology as well as the dynamical model you're running on top of it. So instead of looking at this simple adjacency matrix, that sort of typical approach these days, I'm sort of advocating for this more holistic approach where you take into account both the underlying structure, but also the model, the dynamical model you're using on top of it. And that's why I'm calling this the structural matrix, which is a real structure you're assuming by running that model. So again, so this may sound like a little bit too good to be true. So let's start from the very simplest, humble beginning, the unbiased random walk. So you probably already remember these equations where you have these stochastic matrices from Markov chains. You can actually build a continuous system of that, but let's use a more intuitive example. Thanks to Martin Roseball, so I used his demonstration a lot. So here's a simple demo of a random walk that's walking. So let's get it started. As you can see, this little dot is traverse the system. Every time it hits a node, it flips a fair coin among its all neighbors and just take uniform and random, jump to the new destination. And just keeps go on and on. So let's speed it up. And let's make the node size and link size be proportional to the frequency that they are being visited. So this is a simple idea. And if we switch to this histogram, basically counting the frequencies that each vertex is being visited by this random walk, you can see, I think you can see clearly here that it's approaching this sort of white box, which we call the stationary distribution, that's defined by this network structure already. So we'll let it run for a while at the background, and we'll get back to here. But as you can see, it's slowly approaching this stationary distribution. So the idea now is try to connect the centrality measures as well as the community structures using this unbiased random walk. Well, first step, centrality, the degree centrality pops up to be a direct map, direct hit, because the stationary distribution is exactly proportional to no degree. It's kind of easy to understand as well, right? Because if you have more edges, you're more likely to be visited, and that turned out to be proportional in the convergence of this random walk. And for community structures, the idea is a little bit more complicated, but still, the idea that these clumps of nodes that's supposed to be in the same community will be visited by the random walk all together in a period of time. And to jump between these different communities will be a rare event, right? Because whenever you visit this border node, you have a much higher chance of going back than cross because the structure of community that we have assumed. So this idea, now I think now we can see that clearly in this demo as well. So as you can see, it's pretty much the random walk has converged, and the size, which is the frequency of the visit, has now been proportional to its degree in this case. So degree centrality pops out. And this division between these orange and blue communities can be thought of as this graph cut across this boundary where these edge weights are relatively thin. So you can try to optimize this graph cut by minimizing this flow cut heuristic. But the idea of community structure, centrality, and random walk has now all come together. And in fact, there's sort of classic Chigur's inequality, which I'm proposing here, which is a little bit more complicated. Basically, it says this bottleneck between these two communities is bounded by the second eigenvalue of the adjacency. Actually, not adjacency, because we're moving away from adjacency, from the structural network, which is the random walk stochastic matrix. So that's all good, right? We have this sort of unification of these three ideas. but under this very simple model of unbiased random walk, there's only so much we can do with it. So can we do better? So now we try to generalize these simple random walk to more complicated dynamical models. The first step is that we can bias the random walk using this bias matrix B. It can be simply shown that, by this matrix multiplication, your chances of moving to a particular node are now proportional to its bias. So that's one possible generalization. Second generalization we consider is what we call the vertex delay. So it's a little bit different. Now we have a delay matrix called tau, which multiply outside of the whole Laplacian, random walk Laplacian. By the way, dA, d minus a, parentheses, d inverse 1 is the stochastic matrix you're familiar with. Now, it's the random walk Laplacian associated with stochastic matrix. But if you multiply that by another matrix, delay matrix, you can now model this delay, which essentially says when the random walk traverses the system, it's not going to do like what you're doing here, sort of jumping at a constant rate. Now, by introducing the delay, it can wait for a longer time at a particular node as you wish. And that's sort of the second generalization under this framework. Putting all this together, we have what we call the parameterized Laplacian framework. So we have the bias, we have the delay, we have the surcing, which turned out to be not as important as we first thought anymore, so I can ignore that. It allows to connect to not just random walk, but sort of distributed computing consensus processes in other applications. And these different random walks, the unbiased one, the delayed one, and you're seeing some other like max entropy random walk, can all be connected through these different kind of parameterizations or transformations using these matrices. And this is the parameterized Laplacian framework we proposed a couple of years ago. And under this framework, you can sort of recover a lot of special cases that has been shown previously in those two lists. So you have degree centrality as the base case. You also have the eigenvector centrality. You have uniform centrality. So it's not covering everything, but at least some part of it. And we have this parameterized conductance corresponding to the conductance, which was one of the community detection algorithms I mentioned before, as well as replicator. And in our paper, we basically proved mathematically this Chigger's inequality still holds. So the classic spectral methods can still work after these generalizations. In fact, this is the most recent work I've been working on right now. And we are aiming to further generalize this random walk, or what we call the conservative process, to a self-replicating process, which will enable us to model epidemic spreading as well as information diffusion. Because at those settings, you don't assume that total probability is always 1. Basically, you produce more, you lose something. And that generalization will turn out to unify the third change of basis transformation I skipped previously, so it doesn't matter anymore. It's now all unified. And it actually covers all possible linear operators in the space defined by these graphs. So this is ongoing work. So the next step, I will be trying to use techniques like quality distribution analysis, multi-time scale analysis to establish computer structure as well as centrality in these new cases. But now let's take one step back, because you're probably now sort of overwhelmed by these equations in mathematics. But the cool part of this framework is that all these complicated maths can be explained or visualized by graph transformations. So here I'm showing the bias transformation can be visualized. Basically, you increase the weight of the nodes that you're biasing towards. So in this case, I'm using a bias random walk that's biasing towards high degree nodes. So that's why the edges between the high degree nodes are now twice as thick as those connecting low degree nodes and high degree nodes. Second example, I'm showing the delay transformation. That's even simpler to understand, basically at a self loop. So if you're waiting, if you specify a particular node to have a long delay, you might as well give it a corresponding self loop so that by chance it will stay at itself at a specified time. So these two graph transformations allow us to incorporate these two generalizations by just basically changing your graph. And you can composite these transformations on top of each other, basically producing complicated models that you're sort of trying to build in your mind. It becomes a sort of a data pre-processing step. So the beauty of this is that now, because we're only playing around with data of graphs, does not relate to any community structure detection algorithm or centrality measures anymore, because by assuming these transformations, and by assuming a sort of corresponding dynamical process on top of it, you're gonna produce the real structural network. As a result of that, then you can throw the favorite tools of community detection or centrality at a new transformed graph, and the intuition still holds. So the catch here is that to make this magic work, you need algorithms that work with weighted graphs as well as self loops that's allowed. So here's an example of how you can do this in practice. So suppose you have a data set and you think, and you try different centrality measures, and eigenvector centrality pops out being sort of a better choice that makes a lot of sense to you. I can imagine this being sort of a, say, causal network where, if you contribute to a lot of work and your indirect collaborations will also count using eigenvector centrality. So now the next question you ask is, by using eigenvector centrality, so what dynamical process I'm assuming, right, according to this framework? Well, there happens to be a maximum entropy random walk, which is basically the bias random walk with a bias proportional to your eigenvector component. And if you run the dynamical process, you'll find out the stationary distribution turned out to be eigenvector centrality squared. So if you're all you care about is ranking, then that should give you the same order. And that automatically give you the next step of the best, sort of I hesitate to say best, but sort of most appropriate matched community structure algorithm that associated with eigenvector centrality is the conductance. And you can go back and forth. For example, if you really care about the absolute value of the ranking, right? So it's not just the order of the node that's important, but how much one is more important than others, then you might reconsider and use actually eigenvector centrality squared as your new centrality measure. And say if you wanted to run like an epidemic process on this network, instead of using random walks, you should then ask your own question of what's the corresponding centrality measure as well as community structure algorithms you would choose. So that's sort of how these different pieces now, or integrated in the same framework, will interact with each other and sort of give you a guideline of which one is working and why it is by interpreting them using these dynamical models. So that's all fine. Sounds very, exciting. But how do we put this into real use? So this is some of the collaboration I've started here at IU. So here's one sort of particular work I'm collaborating with. I'm not sure if he's here today. I don't think so. With Ian and YY. The goal here is because in a lot of community structure detection algorithms, like here, we are looking for a hierarchical structure, and you're not necessarily satisfied with the fixed resolution. So in this example, if you want something like this, right, you want finer details in these groups, but you want to keep these guys same in the bigger group. Usually that's not possible in traditional community detection algorithm, because you cut the dendrogram somewhere that's same for everywhere. In this case, we can do this trick by introducing the vertex delay, or self-loop, according to the graph transformation idea. What it does essentially is that when the random walk traverses the system, so by the way, these communities I think is produced both by the map equation built by Martin Roosevelt, which I used his demo. But by changing the delay factor at these local regions that you're interested in finer structures, basically you make the random walk much slower when it enters these part of the graph. And that would naturally lead to finer separations of group structures in those regions. So the difficulty in this particular application is when you try to scale it up to millions of nodes. And it's a challenging task when you're talking about continuous random walk. So we are employing some kind of approximation, and hopefully get it to run on real big systems. The second application of this framework is my collaboration previously with UCLA, is Katie and Andrea, and this is about I think this data set is about handwrite recognition. So basically, I think it's the data set where you have 4 and 9. I think this blue one is 4 and the red one is 9, the handwritten by people. And these are image pixels. So what happens here is that we map them into a higher dimensional space, sort of classic clustering approach in machine learning. But we took the graph approach because we want to separate them, but it's measured by their relative distance in this space. So here we tried several different special cases under this framework, including normalized Laplacian and the replicator, and they give sort of different flavor of the separation. Basically, what happens here is that normalized Laplacian has a better sort of detection of things that really look like 4 and really look like 9. But it's a little bit worse in the boundary, because the real boundary looks like down here. But if you try to optimize over that, but you end up overfitting, so you lose some false positives of 9s up there. So it's a trade-off. And so it's kind of a message I'm trying to send here, is that there's really no best measures you can pick. It's really, trying to error, and then you have to play around with it. And then our framework allows that by tweaking these little parameters that you can play around with. An ongoing collaboration with a colleague Borner here at IU is I'm trying to combine this scholarly network of collaborations and these geographic networks of transportations to build a better predictive model, if you will, tells how do academics collaborate, group themselves into communities, and so on. So the idea here is that this dynamical model still applies under the circumstance. So if you look at here, when people build these multi-layer networks, it's very typical for them to assume sort of a constant connection strength, just for the mapping. But if you really think about it and assume a random walk process that's walking on this structure, then it makes more sense to make some of the nodes, high degree nodes with stronger weights, because that's really actually the null hypothesis that everybody is as equally likely to cross the layer. if you make everything the same, then those with higher degrees would actually very low probability of crossing the layers. And there's so many ways, so we're just exploring our options here. How do you combine the different matrices by building bigger random walks, dynamical systems. You can have matrix sum, you can have matrix product, you can have Kronecker product, building higher and higher space. But so this is what I'm talking about if you want to go this multi-layer approach. So besides the sort of random walk modeling of these interlayer connections, you also be careful about the heterogeneity in every layer, right? Because imagine this is airlines, trains, and buses. The way they are connected follows the way your transportation happens on each layer follows very different rules. And when combining them, before you combining them together, it's a good idea to use some of the transformation I described so that now they're all under the same model. And now it makes sense to stack them on top of each other. So let's try to throw, so this is kind of the brainstorming session, I guess, because I don't really have results yet. Throw these ideas of combining these networks into this motivating example I have. So an obvious one is we don't even take into account of the second layer of transportation. Basically, we break it down into parameters to use to transform the coordinate network. You can do that by the bias transformation I talked about, and you get that. You bias towards this group of people, and those people becomes much more important. So that's one approach. Second approach is that you don't bias towards certain vertices, but you bias certain edges. In this case, you consider the collaboration between this group and that group be very important. So now these gray edges becomes twice as thick. So you can imagine, so I'm just showing toy examples here. You can imagine these parameters of biases and delays coming from metadata that's associated with each node. Like their age or their productivity, things like that. And here's an example of the multi-layer approach. So I'm sorry, so here's a sort of different data set, but we have 3 groups, people collaborating with each other. On top of that, we have airport connections. So I was able to map some of the geolocations and shows and sort of connecting these 3 groups together by these airplane connections. And in the first example, is the way I build it, I think it's using unbiased random walk, and I give uniform weights actually across the different layers. And it turned out this group of people, if you really try to bisect this network, it turns out these 2 group people are closer than the third group over here. But then if you apply the transformation on this side, where it takes account to the geo distance and so the air flight transportation capabilities to transform the distance, then you have a different story. Now in this case, this third group becomes more separated than these 2 groups. Because as you can see, while this only have one connection from this group to that, but that actually turned out to be the same node, which is IU. And the geodistance between IU and IU is infinite. So this really push these 2 groups together in this case. Where in this case, I think I've penalized this sort of infinite distance measure, and it can only help you so much. So then it turned out that these multiple connections actually wins this time. So this is a toy example. So it's sort of try to motivate what we are trying to study here. And we have a very ambitious goal in the long term, and by combining these different data sources, you can imagine we can try to predict who your best collaborator will be if you move to a new location. You can try to predict your next citation if you replace this with a citation network based on who you previously cited and as well as who your friends are citing. So there's a lot of things can be done here. But we're facing a very challenging problem at the moment, basically data cleaning. So it just turns out my ambitions now all hang on the thread if we can clean up this data. And as you said, in any data-driven research, you spend 80% of your time cleaning up your data, right? So here you can see, this is I think part of the Web of Science data set we've extracted. And if you search for author Alex Vespagani, you got like I think like 36, if I remember correctly, different aliases for him alone. And you have to somehow entangle this mess. And there are algorithms out there, but the most satisfactory ones so far is basically hand correcting, and that's what Anne did, who is also a member of our institute. But this data set is much bigger. It has millions of publications, so we would really want something better than that. And also, there's noisy data entries in the geolocation as well. As you can see, there are so many different airports. Most of them didn't even, use in our everyday travel. And this whole idea of doing modeling dynamic processes on top of network structure is very powerful. It also allows you to do this sort of localized clustering. So you can imagine, so let's see how our random walk has proceeded so far. So I guess we need to restart it just to show this point. Reset. As you can see, so if we stop early before convergence of random walk, the process will only explore a local region that's close to your starting point. So that's a limitation, but it's also a benefit, because sometimes you don't care about the global system. So that's what happens here by starting the random walk at different parts of the graph, and stop early, and you'll be able to pick in local structures around those regions. And I guess that's all the slides I've prepared so far. Well, I welcome any questions and suggestions. Please.
Actually, I didn't understand fully the mathematical part, but I just wondering, so you mentioned structure and dynamics, right?
Mm-hmm.
And I also want to consider semantics, which means types of node or types of connection. I think you gave us an example of collaboration as well and transformation as well, right?
Mm-hmm.
Combine them. I'm sure that X as a transportation and H as a collaboration is pretty much different, right?
Yes, exactly. So this is the tricky part. So in here, I'm proposing you to transform different layers so that they match the same underlying process, and then you can combine them. So that's only possible if you sort of have homogeneous layers like transportations, right? Which you can assume there's always people traveling on planes as well as on trains. But if you consider one layer to be co-authors, the other layer to be transportations, it becomes less clear. So I don't think I have an answer to that. It's more a sort of application. The way, really your decision of how you want to model that. And I don't think the current framework will be able to address that mathematically. But that's a good point. Sort of exactly what I'm trying to convey here is this heterogeneity in terms of edges as well as the nodes. So it's a baby step. So we unified some simple random walks, and I'm trying to unify some epidemics. And it's only, part of this long list, right, I showed earlier. You can check off, I guess, this. Not quite this, it's a little bit different. You can check out uniform degree eigenvalue centrality. PageRank can be built using a different graph, but we're getting there. So I think it's important to build both empirical approaches, sort of what's the best practices in application domain where people know what they're doing and know more methods they can choose from. But it's also important for us to develop from a theoretical perspective how these things are related with each other, and how in this case, how do you transform one to another, right? That gives you understanding of why they're giving you different results. Go ahead.
For the 4 versus 9 handwriting cluster,
Mm-hmm.
what is the graph there? What are the edges? Is it like a complete graph, or is it every?
It's a complete graph. Okay. So exactly. Essentially what they did, so in this case, we're also failing the scalability issue if you consider complete graph. So I'm showing like 2-dimensional space here. In practice, they project this into some kind of dimensionality reduction by choosing how many eigenvectors you want to build into your features. They used Ginsburg-Landau functionals to approach it, so that they're mathematicians, so it's even more inaccessible than my stuff. But the idea is that then you do the clustering. And these different special cases basically essentially give you a different projection of this space. And it's not the most exciting, intuitive, explanation, but helps in this case to explore different distance measures in this case.
So my graph has n squared edges.
Yes. So you do start with a complete graph. This is not too big. It's like, I think, forgot, 90 by 90 pixels, or it's a simple digit handwriting. So it's a toy example in this case.
Every dot is equal to every other dot?
Yes, so we're building a higher dimensional space, basically embedding the distance of these different handwritings based on how they're similar with each other. So the matrix is not the pixels, it's the samples, between the samples of these handwritings. Go ahead. Mm-hmm. It's a good question. So if you generalize beyond the parameterize the process I talked about today to self-regulating process, which is future work, there's no global convergence anymore, right? Because you're exploding or you're shrinking, and that's why in that case we have to talk about quasi-stationary, basically conditioned on total mass or certain ways to find out structure just beyond these global exploding trends. So in that case, but we always look for some kind of a stationarity to do our analysis. Sure. Well, because what Laplacian does, it models this dynamical process in continuous time. And there's, in this case, particular case, so if you read into this Laplacian, let me show the simplest one. I think I have this one on my slide as the simplest. The random walk Laplacian. So if you expand out this matrix by hand, you will see what shows up exactly these difference equations. If you're working in discrete time. And basically this probability going from node U to node 1, like say node 2 to node 1, if you taking a random walk, unbiased one, is basically the number of edges, the weights of the edge connecting from 2 to 1 divided by the total degree. Right? That's assuming it's uniform and random. So that's how it worked out there. So that's the AD inverse part, if you were talking about the column convention. In continuous time, however, you have to add back in the amount you lose. Basically, it becomes a difference equation in discrete time. Essentially, it's not just how much you're getting from your neighbors, but you're also losing to your neighbor. So that's why Laplacians are built that way. And they're nice because you can study their spectrum. They have nice spectrum properties. The eigenvalue and eigenvectors tells you a lot about the network structure and their stationary distribution. And that's what a lot of the classic dynamical system theories are built upon. So that's why we're trying to connect them there. But please don't be discouraged by these mathematical difficulties. What I'm trying to tell here is that we've done this mathematical work for you. What you have to do to incorporate these delays and biases is by transforming the graph, adding self-loops, making edge thicker, according to some of the tools we already built. So you can find what I have here. So maybe if we have more time, I can try to demonstrate this using my one of my apps software over here. So I've built a plugin for Gephi, which is a popular visualization platform. And by the way, you can find this in my GitHub page. Oops, it's already popped up. Which you can get to from, well, here. You go to iUni, which remember the website iuni.iu.edu, and so I'm over down here. It's kind of complicated, but personal web page. Here's the download of my codes. You can go to my GitHub publication page. So so that's for another paper, but for this paper, I've already compiled everything to the Gephi standalone, so you can run it just like this. And so I'm going to show an example that I just show in the slides. So essentially, that's what's going to happen. So this is the coordinate network versus geolocations on top. And it's a little bit cramped here in this laptop, but so let's try to first build the mapping, geocoordinates. So we map from the authors to their geolocations. And this is done by essentially looking at stated addresses in their publications. Then you can calculate the geodistance between the different geolocations. You create another network on top of that. So once you've done something like that, well, so there's some building tools. I'm not sure how you're familiar with Gephi, but it's a wonderful tool. You can filter out disconnected nodes using this giant component filter. Something weird is going on. Okay, that's good. No, it's not filtering for some reason. Select it. Oh wow, technical difficulties. Well, the gist of that is then you can try to apply some of these special cases to see what kind of structure you get out of it. But this, without pruning out the disconnect components, you're going to get something that's very boring, like, is it running? Yeah, something boring like that, because it's disconnected. So that's not very interesting. I see, it's not. Let's try a different data set, I guess. So the good old Karate Club network. So in this case, every special case is going to give you similar things, because it's very simple. But you can transform this graph, say, proportional to its degree. So yeah, you added some self loops down right there. So it's adding delay factors proportional to its degree. I don't think that's going to change much neither, but it's going to change the ranking for sure. Yeah, no, it should give you a different partition now, because these guys now switch to the other side of the network because of this new transformation. So you can play around with these different data sets in Gephi if you're interested and see what you're going to get. So as I said, we're not advocating for best community detection algorithm or centrality ranking. It's a choice. The power of a choice is what we enabled in this framework.
Thanks again.
No problem.